Dear students, here it comes. This is the review lecture you have been probably waiting for. As I promised, this is going to be a video, so you could visit it at your convenience, most likely today, tomorrow, or during the weekend before the exam, so it will be helpful in a way for you to prepare your exam. I will keep it short. First of all, it will be something around 35 to 45 minutes, and I will not be able to review the whole thing, even the most important things during the past 6 weeks, because it's a lot, and what you have learned is already a very, let's say, solidified version. So basically, the most important concepts are all there, but you would also be able to always distinguish which are even more important. So with this 45 minutes or so, we will not be able to cover the whole of it. What I would like to do is actually to provide basically a kind of appetizer for you and to show you how we're going to do the review and to be able to basically connect the dots, as I told you. And I hope you could just borrow the spirit and maybe some methodology, maybe some kind of even tools I will show you, and to do your own stuff. So do your own connecting dots exercise and really finally get the knowledge that you've learned within the 6 weeks to become one piece or to become, connected and network. That will make sure you don't lose them easily. So you probably, with a very loose kind of dots separated into your mind, you could get away with the exam, but then you basically forget it all 2 weeks after exam. So that's not the way we want it. The way we want it is that you still could really keep some most important knowledge in your mind, maybe not exactly some numbers or some definitions, but you should get the concept. You kind of get the most important, let's say, mechanisms or thinking and conclusions in your mind. So when it comes to a point, you're going to need some knowledge from material science and engineering in your future, let's say, study or career in a company. You could bingo. My professor, when I was doing my bachelor in the second year, told me, this is about something heat treatment to make my material better, or cooling rate should be higher. Then I could get some fresh martensite to increase the strength. And that's the thing we wanted, because that will finally help you. Not just the exam, of course, the exam is important, but there are many more important things in your life than the current exam. Okay, so I think that's a brief introduction of this review lecture, and now I'm gonna basically show you what we're gonna do in this lecture. So in this lecture, actually, I'm gonna show you first some slides we have already seen during the day one lecture. You probably didn't realize them at all at that moment, but now, you just look back them with your knowledge that you obtained during the past 6 weeks, or even less than 6 weeks, let's say. You could really get a very good sense of it. This is a feeling that you will definitely celebrate, because then you see your growth. And followed by that, I will show you some typical way that I'm going to do to connecting the dots. So I'm going to show you with this famous diagram you have been seeing many times, and that's one thing to show you. And the other, I'm going to show you something like more detailed. You can call it process map or mind map, for you to just connect all the, let's say, knowledge into one piece of network. And finally, I'm gonna go back to the survey that Wenqi just pulled out for you, that we ask you to send your questions about any knowledge, any kind of concepts that you don't feel very comfortable with and you would like to get some more explanation from my side, I will just go back to those lists and try to give you answers one by one. All right, let's get started. Let's begin with some slides that I showed you on our day 1 lecture. At that time, you probably don't really remember or don't really realize what all these things are supposed to mean. You know a general overview, you know a overall picture, what I just showed to you. But I think if now we look at back all the slides and all this content with the knowledge that you have obtained in the past few weeks, I think then you would have a very good, fresh, and fulfilled kind of overview, much more vivid than your day 1 lecture. So now I try to go through with this very basic slides again for you. Hopefully you can just try to go through the detailed slides afterwards, and also our reading book, textbook, where you can get much more detailed information. So we said, what is material science and engineering? I think at the very beginning of the course we said materials and engineering. Material science and engineering is an area that is from the overlapping of physics and chemistry. And we gave a very short, limited list over there. You probably didn't realize how much that meant. But I think now, with our courses from this few weeks, that made probably a very good impression for you. If you just look at those few keywords that are listed here, you can see solids, atomic bonding, electron behavior. These are all the things we have been talking about, right? Microscope, thermodynamics. We didn't talk in detail, but we scratched a little on the surface. So we didn't talk about too much on quantum, so that is very slight knowledge when we were talking about atomic structure. So kinetics is always there. So we have diffusion, which is a kinetic mechanism. And when we talk about creep, it is also related to kinetic. So everything is correlated to each other in all these different courses. And of course, we didn't cover many physics or chemistry concepts, but somehow our topic is really built on those fundamental knowledge that you got from your high school or very basic university study about physics, chemistry, and even mathematics. Yeah, so it was not really listed here because those mathematics is already a subcategory of certain physics. But I think you also realized we need your knowledge from calculus. We didn't talk too much about tensor matrix. Of course we could, but since you have solid mechanics and continuum mechanics lectures, that is excluded from this session for you. I think this gave you really a good kind of knowledge scope of material science and engineering. Then we moved on with our very basic important concept about material science engineering, which is about this famous tetrahedron: process, structure, property, performance. So if you forget anything from this course, please remember this. This is really the key element or the key chain of material science and engineering. And then we gave you a definition or kind of a characterization about material science and material engineering. They're in general the same, but as you know, what is science, what is engineering, we have already talked about that really very at the beginning on our introduction course. So I think you know what science and engineering, these two terms differ. That is also a reflection you could find when we just talk about this tetrahedral. So for material science, we're more focusing on the relation between structure and property, and also all the fundamental knowledge, theory, models, characterization method about structure and property. That's why you probably also realize we spend really quite some energy on these two terms. And for structure, it involves many fundamental knowledge like physics, even chemistry as well. And for property, there's quite some mechanics, physics as well. So even mathematics, so they're all there. And of course, after you master those two correlation terms, what you can do is to do a design or discovery of new materials with new properties. That's the kind of two important elements about material science. And in the past week, week number 4, I guess, you finally moved to the part which is more focusing on engineering. So that is the correlation between performance and process, and the process back to structure. Excuse me. So the process to structure is actually rather fundamental as well. We didn't go that fundamental, but you could. So in general, these two connections or these two elements are a little bit less fundamental, and they are more engineering orientated. The goal for you learning these two parts is especially to serve our engineering purpose, which is to create new stuff, right? To create products with the existing materials or develop new material processing technologies. So these are the two fundamental aims or goals for material engineering. I think from our last piece of elements that we got from this Tuesday, you finally get this full picture about this tetrahedral. If you just look at this outer layer, this is more like a kind of application examples or a little bit substantial reflection of this tetrahedral you could really do in the reality. So when you design material, you think about the alloy, and when you just do your material engineering, you think about select. You select from the existing materials. All right. And this is a very important picture, or very tough picture for you to understand when you were just on our first, or let's say one of the first. I don't remember, this was given on Monday or Tuesday for our first week. I think it's on Monday. And you don't really realize what we're talking about here. So we're showing you one diagram. The x-axis is so-called cooling rate. You probably didn't know at that time what cooling rate really is referring to. I think now you know it's very, very well. And the y-axis is about hardness. So maybe you remember, this is Brinell hardness. And this is so-called property. So this is a correlation between, let's say, process and property. It's not the direct connection that I showed you, but this is a rather indirect, because process will decide so-called structure. The structure finally decides your property. But for engineering purposes, sometimes you could just overlook the structure. You don't need to know what structure it is, because for engineering purposes, we just need to focus on property and the processes. Then you can design your product. You can design your processes with that. But let's just look at a little bit detailed of this figure. So it tells, so of course this is referring to a steel alloy in our context, but actually you can also go to other alloys to draw such a figure. And this is a very application-oriented example. So when you just work in the future, for example, in a steel company, in an aluminum company, zinc or magnesium company, when you just try to design your material or produce your material, you always need to look at such a diagram on a similar one. Yeah, because your supervisor, your customer will come to you and say, look, we want to have a very strong aluminum magnesium alloy, and we're aiming the hardness of certain number of hardness. Yeah, try to produce for us. We don't care what exactly microstructure it is, and we just aim at the product. Yeah. So you, as a material engineer working in this company, you should know what microstructure you are aiming at and what kind of cooling rate. Of course, it's not gonna only about cooling rate, but cooling rate is the key factor for your processes. Yeah. Then you can finally deliver your task and deliver the product to your customer. So this is exactly what you probably will be doing if you're in such a business, right? If we're talking about steel, let's say you have such a diagram already. With your knowledge that you got in the past weeks, you exactly could understand what they are. For example, if we just look at the very slow cooling rate, so very, very slow. So what we get here, and probably you remember, we have the process with the slowest cooling rate, or almost not cooling. Yeah, that is the spheroidizing. What you produce after that is the spheroid. Yeah. So you have the ferrite, and you have this very small, or rather small particle cementite. Yeah, it is very soft. Yeah, and that's why you have rather small hardness value. Yeah, and when you just do not use that slow cooling rate, you go a little bit faster. So something like full annealing, so that is already faster. So you are just cooling with the furnace, right, together, and it is already much faster than the spheroidizing, and then you will get this nice large grain pearlite structure, yeah, plus your ferrite. So that gives you a rather, compared to spheroid, it is harder, but relatively still soft face. Yeah. And if you just further increase your cooling rate, what you get? Yeah, you get martensite, right? So this is the very fast cooling rate you can see here. But you could have two types of martensite. Yeah, if you're aiming super hard, yeah, super high strength martensite, you can choose to have we call it a fresh martensite, or in your textbook it's just called martensite, which is this needle-like martensite and very tiny microstructure, very distorted crystal structure with the BCT structure. And of course, I mean, from the same cooling rate, but if you just try to do a little bit post-processing, a heat treatment with quenching and tempering. So quenching is already there, yeah, because martensite itself is quenched. What you need to do is just a tempering. You will get so-called tempered martensite. Yeah, this is exactly how it looks like. You have ferrite plus very small, tiny cementite. Yeah, so if you just compare these two, so I think I asked you during the course, what is the difference between the tempered martensite and spheroid? They're both ferrite with base and a certain cementite in a rather particle form less than a laminar form in a pearlite. They look similar, but why they differ so much? Yeah, they differ due to the size of the particle. If you just look at the scale here, so the particle you look at in your tempered martensite, although they're both cementite, are much smaller. Yeah, so that's is the key element to increase your strength, increase your hardness. Yeah, I think this is a very nice figure for you to just reflect many things we have learned in the past few weeks. It is giving you much more rich information than we just talked about during the day one, right, lecture. So try to correlate all this by looking at the slides back again. And then I want to show you a different materials that we have investigated. We showed this to you at the very beginning. We will talk about metals, ceramics, and polymers. And I think we touched all of them when we talk about structure. Especially we try to correlate certain atomic structure, atomic bonding with certain types of materials. And we also correlate a little bit about crystal structures with all these different material groups. And when we just go to properties, they are still kind of showing you certain information, but with a less resolution already. When we talk about processes, we didn't really touch too much about ceramics and polymer, then we focused on metal. Actually, for those two, structure and property part, we also focused mainly with the metals, because we want to give you a chance to look at the full picture, the full connections of those four elements in the tetrahedral with one type of material, which is metal, and you can really get everything correlated for that tetrahedral with this one material. And next week we will actually give you very brief and quick overview about ceramics and polymers, and you will see how their structure looks like in detail and how their properties will be in generally looking like, and what are the processing methods we're using for those two materials. So the level of detail will be very less compared to what we traded with metals, because it is not possible for us to trade with the same level of details within this short period. But it's good for you to know how they will be, and of course you can also discover further when you just read the textbook. Yeah, and then we also focused on different property types, and I gave you, we will have 6 major properties, and so far we have been mainly focusing on mechanical, and that is also the idea, the same idea is applied here. So we want to just make sure everything is going to connect it in the tetrahedral with one property, one core property, and the rest of them will be a little bit similar. And as mechanical is the main important property that your major should care about, that's why mechanical property is the key point that we focused on. I think, for example, some of you are from electrical engineering, School of Electrical Engineering, and you are probably interested in some electrical properties, and of course also the rest. This will be also briefly covered next week, and you will see how those 4 kind of connections will be about, and when we just talk about different properties. But that will be very brief, as I said. Of course, these are the 6 key mechanical and the 6 key material properties, and if you just look at this wheel here, you could have actually a lot. Yeah. So we also touched a little bit, for example, density. We talked about quite a few words over there when we talk about the crystal structures, but in general, we touched only basic elements of this rather comprehensive will. So of course, you could find more information about them in the textbook, and you will also learn them much more when you go to your master level. And finally, I want to show you this lecture flow again. So if you just missed, I think that was shown for our Monday lecture and was again on our Tuesday lecture. But I noticed not so many of you attended both sessions. That's why I tried to include here and gave you a overall flow again. Our lecture, the whole 12 sessions, let's say, are actually very nicely connected via this tetrahedral. I will show you how. You can also work on a little bit details after I show you how. So we have these 4 elements, you know them, and the key for us to learn is one by one. First, the connections, but how they're connected are not by these words, right? The connection is defined by these 3 main terms. One is characterization, one is theory. So characterization, we're mainly talking about experiments, methods, and data, so measurements. And theory is all these definitions, equations, and kind of qualitative correlation. Yeah? And modeling is something you mainly experiencing, let's say, during our exercise sessions, at least for the first half of the whole lecture. So you see all of these 3 are included in our lecture. And then this is also the core you are trying to get each session. And then we try to get the connections. So for the structure part, probably you remember we started with atomic structure. You try to recall all the knowledge there about electron and atomic bondings. And what are these bondings existing or how they are different when we just talk about different materials. So these are the key information for you. And then we moved on from, let's say, 2 atoms, because when we talk about atomic bonding, it is relatively focused on 2 or let's say multiple atoms. But our material is not just by few atoms, right? It's thousands, millions of atoms. So we zoomed out a little bit from atoms, and now we're looking at a lot of atoms together. Then we need to talk about the crystal structure. So how the atoms are stacked together to form our materials. Yeah. But during that lecture, I think you realized the difference between the crystal structures and what they will influence certain mechanical properties. For example, even the density. And then I think the most important part for you to realize is this crystals are the so-called grains in your microstructure, in your material. They are not just one, they could be multiple, right? And when you even have the same overall, let's say, material, but their crystals could be also different. That's why you finally have another definition, which is called phases. Yeah, for example, if you think about the certain steel grade, you see it as a steel, and they are all BCC. Yeah, but their crystals are different not only from crystallographic orientations, they are also different from their basic arrangement in terms of the carbon interstitial composition. Yeah, that is what we're talking about. For example, difference between pearlite and ferrite. So they could exist in one certain steel. That is the final level we're talking about structure, which is not given at the very beginning, but a little bit later when we talk about processes, right? But that came with a reason, because you need to have some basic knowledge. But now, if you try to take that back to the structure level, you actually see a very beautiful picture, right? We're just zooming out and out. Of course, if you zoom out further, you see your material as a macroscopic piece of material, and then you could do characterize on the properties, right? And we've started with elasticity and went quite deep to plasticity, and here we really try to find out the mechanisms about elasticity and plasticity. We go back to the structure level to give you the mechanism about these two observations. Of course, you learn the hardness very quickly, but as a very important engineering measure. And we kind of focused quite a lot to failure, because it is such an important measurement for our engineering materials. And this is something we would like to definitely avoid. We could be a little bit less efficient with our material choice, but we don't want to risk for any failure. And the last thing about property will be physical properties. So here they will be referring to electrical, thermal, magnetic, optical, and so on. You will visit all this rather in a poster fashion, you will see next week. And that's all about properties. And then we know if you just take properties into a group, you would formulate so-called performance. Yeah, because properties is something we try to define on a single level or single material. But when we just talk about performance, usually it is an integrated level. So we're not just talking about brittle failure, we will talk about brittle and ductile, we will talk about fatigue altogether for one material. And more importantly, it is about rather a product, not just a material. So this is just zoomed out again. Yeah. So we're not just talking about a tensile specimen. We're talking about a turbine blade, for example. Yeah. So this is the whole kind of spectrum. When we just zoom out and out, you now see it better. And finally, we stopped with just our imaginary world, as if all the things are exhibiting themselves to you directly. No, because we have to make all the stuff. That is the essential part of process, how to produce our stuff. Yeah. And over here, you could know the process is the way to just realize your performance. Yeah. So how do you want to design process is fundamentally decided by your performance indicator, and which probably came from a designer or so. For process, we introduced you 3 very basic principles, which are diffusion, phase diagram, and phase transformation. As these are the prerequisites for you to get the final point of process. And in the end, we showed you the major processes. Let's say if you want to just get a product, we showed you rather with a live demonstration, which is how to produce a kitchen knife. Of course, our resolution over there is pretty general, but I think it gives you a good idea and good overview about how things are produced. Yeah. And during that session, I think you also know process will finally decide your structure, as I just showed you in the previous slide. So that was the nice loop we have created via metals, maybe you remember. Yeah, we focused really only on metallic materials to demonstrate how this loop is running. And in the past week and also probably this week, we said we're going to give you two add-ons. And the first add-on was already illustrated here. Basically, we focused on, let's say, the structural part and also with a rather weak connection to properties. And we focused on ceramics. So you learned how ceramics basically look like in terms of their basic microstructure from all these three levels, and also why the ceramics are creating a strong, let's say, strength, but rather brittle fracture behavior. And followed by that, we also got the second add-on, which I spoke already a little bit in the last line. It's about the physical properties. So we focused on thermal and electrical, with more, let's say, kind of emphasis on thermal, because that is very much related to engineering applications. And you learned the quite important phenomena or concepts about these three items about thermal properties. So that is something which is important, and you will also see them in the exercise and exam. All right. Good. And the rest is rather a kind of your reviewing. I'm trying to give you a really a appetizer for you to prepare your exam and review what you have learned. This is a way that I like the most to study new stuff. So you try to build up a whatever, could be a mind map, could be a structure map like I'm giving you here, and any other things, but try to really connect all the dots that you have learned session by session, pieces by pieces together, and to see the overall picture. I mean, the previous slide is already a very good overall picture, but it is rather general. I would hope you could develop something as I showed you here on your own to get a little bit zoom in overall picture. So this is one figure taken from the book, which is not a very good one, I have to tell you. But I'm giving you as kind of inspiration point. You can try to design your own. For example, the atomic structure is missing here, but the kind of method is a good thing for you to borrow at least. You start with the structure and you try to connect it with the demonstration that we showed you when we talk about materials engineering. You know this, all these phases. So this is a way from small to big. And of course, we cannot just talk about one abstract material. That's why here the book is giving you example from the steel perspective. Of course, you can think about something from other perspective. And that is about structure. And here is a zoomed in figure about the properties, because you know how all these four elements are connected. Here is rather a zoom in about each element. So for properties, this is really a very brave overview. I think you can do quite better than this one. So here is starting from mechanical properties, and it is trying to bring elements about mechanisms, and it's also trying to touch a few examples when we just talk about our iron and carbon phase diagram with let's say martensite or whatever phase. You can think of a different one, of course. And you can also do the same for the processes. How do you just connect on elements in processes over there? So this is rather, I would say, a okay overview because it touches the basics, but it overlooked the diffusion, for example. Directly started from phase equilibrium, that is the phase diagram, but it includes nicely about those diffusions here. Okay, but that was rather simple. but it includes all the elements when we talk about in-phase diagram, and then the phase transformation with isothermal and continuous cooling, and then it combines quite good with these processes we just introduced to you last week. No, this Tuesday. So different annealing processes and also quenching and tempering. Yeah. So this nice heat treatment processes. Of course, it's not including the casting and forming processes that could nicely enter to such a diagram as well. Yeah, but that is just, as I said, a starting point for you to think about it, to organize your outcome from the course. I think you will benefit from doing such a practice of your course. All right, now we come to the last part about this review lecture, which is about to answer your questions on the survey that Wenxi just gave to you a few, maybe last week or 2 weeks ago. Well, I just took a look at it a few minutes ago, and as you can see, we got only these 2 questions, which is rather good news, actually, so we don't need to spend too much time on this. This is one thing, and the second, it also means you're feeling comfortable with the most of the concepts lectures that I have been teaching so far. That makes me happy. Yeah. And for these 2 questions, I'm going to read for you, so you don't need to kind of read from screen. They're rather small. So I would like actually begin with the red one, the second one, because that is easy to answer. And then we go to the first one, because I'm going to show you that in the next slide. So the second one is, can I have more details on our exams? I like what method, what it carried out, how can I prepare for the R exam? All right, that's a good question. So we already said a little bit during the course, but not in detail. So if you would like to get much more details exactly about what is the method that's going to be used and how we're going to schedule things and so on, you will get more information tomorrow on the exercise session, and you will also be able to read in detail from my courses when they're available. To give you very basic information, we're going to do our exam on Zoom. So basically, you will be characterized into groups, and each group will have 1 hour exam with me, and during the exam, I will be giving you, let's say, informative and simple questions. So they will be not really extremely hard for you to calculate or so, because it's our exam. It's like any kind of our exam you probably did. If you haven't done any oral exam, it's just like, we have a discussion. I ask you questions during the course, similar to that. And how to prepare it? It's simple. It's just like how you prepare your exam. So how you're gonna review the lecture, and how you're gonna basically solidify your kind of knowledge obtained during the past 6 weeks. Yeah. All right, so that's the second one, and the first one is about the coordination number of a cation or anion is the number of atoms physically adjacent to the atom, or the number of atoms having chemical bonds with it. So this is a question actually pretty interesting. Let me just try to show you. Here I just brought the slide when I was introducing you this kind of coordination number for ceramic. And first of all, let me just try to give you an impression again. Maybe after this kind of impression, you already got it, what the coordination number really means. Yeah. We don't need to review the whole thing. I will directly go to the point. As you can see, This column is about the coordination number. Yeah, of course, how many of them is kind of related to the ionic radii. So basically the ratio between the radius of cation and the radius of anion. So we will not focus that. We basically speak about why you're having these numbers when you have such a basically structure. So as you can see here, if we just have a linear configuration of atoms or ions, the kind of coordination number is 2. So the coordination number here is basically speaking, the number of anions with respect to the cations. So for this cation, it has 2 anions. Yeah. So that's why the coordination is 2. And for the triangular one, you can already imagine this is 3. And for the tetrahedral, so you know how tetrahedral looks like. And the cation basically is in the center of it. So if you just look at it from top view, you need to make your first atom on top transparent. Then you see the cation. So it is touching 4 adjacent anions. So that is basically the answer to your question. So the coordination number here, we're especially talking about the coordination number of, let's say, cations, and it's talking about how many anions this cation is in touch with. Yeah, so that's why for a tetrahedral we have 4, and for, of course, a octahedral, this is a little bit more complicated, and we're gonna have 6, and for cubic it's 8. Yeah. This is basically the answer to your question. And if you want to just make a little bit correlation with the chemical bonds, we can, for example, take a let's say for this sodium chloride, and this is a ionic bonding, right? So the sodium is gonna lose 1, let's say, electron, and to the chloride, and then the chloride gets 1, so then we build 1 ionic bonding. So this is the number of the ionic bonding, and this is not the number we're talking about as to the coordination number at all. So for the coordination number, it is really asking you to imagine the crystallography kind of structure. So you have to think about how the atoms are basically kind of in touching physically or kind of geometrically with each other, not about the kind of electrons it is going from one to the other, or how many is going to from one to another. All right, I hope that gives you a clearer impression about the coordination number itself, and also more about basically atomic bonding and also crystal structure. All right, I think that's basically all of it. And what I would like to close for this lecture is actually to bring you something we spoke about maybe on day 1. So as you probably remember, I gave you 3 tips for this lecture. Well, it could be even general. Yeah, it's 3 tips for basically learning anything, for a lecture or for something you would like to get knowledge about. The first tip was pretty simple. Basically, I told you, when you really go to a subject, you start digging and you start learning. It is always something you don't see from the surface. Yeah. Maybe on a day 1, you see this tip of the iceberg, and I told you, be aware, there's a lot beneath it. I hope, although it's only 6 weeks, you really see a lot below it. You really know this world in a, let's say, more substantial way. Yeah. So I'm pretty sure you got that, and this is a nice feeling, exactly as I said, to celebrate. Remember this feeling, and that will make sure you're going to learn basically more and more. And the second one, maybe this is the most, let's say, emotional one, and the one that you felt really most, let's say, clearly. And we said during the progress of your wisdom, and you will also have basically a emotional reflection or confidence reflection. I already warned you, you will have a very, let's say, quick phase in our subject to reach this peak of Mr. Stupid. So you don't have good feeling for a long time, because suddenly you're gonna basically go to this valley of despair. And probably that happened in week 2 or week 3 for most of you. That is okay. Yeah, I think now if you just reflect where you are at this moment, I'm pretty sure most of you are at least here, so slope of alignment. And even for some of you, I think you really get this kind of a pretty good phase. You're getting a kind of plateau, and you know what you're doing, and you know what you have basically learned and how you're going to apply them in some applications, even make a reflection about your knowledge system. But this is not the main purpose. Of course, we want to push you to there, and we want you to be in this phase. But maybe what is more important for you is to remember this feeling. So when you just reach the peak of Mr. Stupid or whatever, when you start to fall, and you don't see the end of it, and it seems like it's endless, I cannot go through, I will give up, and so on. But remember that feeling, and remember you kind of went through it. Yeah, that's why you are here. I think maybe some of your peers, due to various reasons, they had to, just fall further. And we don't see that is completely wrong, because there are always many other different things in your life to handle with. But for you guys here, so I want you to remember that feeling and how you just overcome that kind of difficulty, and how you finally reach this point or that point. That will be probably one of the most important lessons or experiences you're gonna kind of take away from this course. Well, the last tip is this something about 10,000 hours rule. Of course, this is not exactly relevant for this subject here, but I would say this is general relevant. And of course, if you just invest proportionally enough time with the given scope, you would definitely become more and more a master. Yeah. If you just started that early at the beginning of the course, congratulations. You're definitely doing well. If you didn't start really in a very good shape, that is fine. So take the few days, 3, 4, 5 days before exam, that will help. Yeah. You will definitely see some effects about it. But in general, for all of you, I think this something about 130, 40 hours or 50, 70 for some really diligent guys, you put there, you will see the kind of payback, definitely for sure. But this will be also the beginning. Yeah, if you really enjoy this lecture, enjoy the kind of curiosity about this world, and enjoy some coding, enjoy some simulation to see, you basically can run some things you see from your daily life about fracture or so. This is the beginning. So you invested about 200 hours, and if you continue with this lead, you will soon reach this 10,000 hours, and you will definitely become one expert in this field. This doesn't only apply to our course, actually it applies to probably any subject you have been dealing with. So try to find that subject in your life and start building kind of your profile, become expert in a subject. All right, I think that is all that I would like to say to you. And this is also the end of this lecture. I wish you a good luck with the exam, and we will see each other next Tuesday during exam. And but I wish you also a good luck with all the other exams from different subjects. And finally, after the exam, I wish you a good holiday season, and we will see each other in other occasions. All right, see you guys. Bye-bye.